I'm Stefan Crandall. Welcome to PEIMA. Whole bunch of words. What we're really talking about is anomaly detection. New ways of doing it. So, I'm a PhD student from Curtin University. Where's Curtin University? All the way over where that arrow is pointing in Perth, Australia. So it's been a bit of a flight to get out here, I'll put it that way. I work on network security detection with my research team. We've got from Curtin University's Department of Computing, Associate Professor Mihai Lazarescu, Dr. Duxon Pham, Dr. Seating So, and from Oklahoma State University we have Professor Subhash Kak. Now that I've mentioned them, we can get into this. So, denial of service attacks. They suck. They're very easy to use, they're very simple, they're very effective. Basically anyone can start them these days. You'll get something like this in an email from your clients. They'll say, help, I can't access the internet, even though it's just their website, but you know, I've worked in help desk, so. So basically, you know, they're very, very easy these days. Social media lets people coordinate for massive distributed denial of service attacks. We have botnets around, you know. It costs the attackers basically nothing to launch, and it costs you a lot to deal with, especially when they are very effective. This only gets worse. We have the Internet of Things. The Internet of Things to exponentially increase the amount of devices attached to the Internet over the next decade and into the future, and who God knows where. So basically these things we've been seeing aren't particularly well secured, so we're expecting to see enormous quantities of effectively denial of service vectors entering the market over the next decade. So flood-based attacks will become exponentially more powerful over that time. An example of where we're going was the Krebs on security distributed denial of service attack, where we saw over 620 gigabits per second of traffic, which is ridiculous, completely ridiculous. So it's basically inevitable that this is going to get much, much worse over time, and it's going to get much, much more prevalent as it becomes easier and easier for people to leverage this kind of thing. So what can we do? Can we install a firewall? Well, no, because you're actually hosting the things that are being attacked. They're legitimately trying to use them, just abusing their use of them. So we can install an intrusion detection system. Yeah, you know, a signature-based IDS can detect attacks from botnets. It knows that, you know, there's bad IPs out there. You don't want traffic coming from them. But you can spoof IP on the internet, so maybe not. And you could make your traffic look like normal traffic, so the signature-based system can't really tell. Because again, we're not sending, you know, actual smart sort of viruses, worms or whatnot. We're just sending a lot of what looks like legitimate traffic. So you can pretend to be whatever you want. So why don't we teach an AI to do, you know, our stuff for us, you know, an anomaly-based detection IDS system, you know. What if we taught an AI what normal looked like on our network and then tell us when things go wrong, when things aren't normal anymore, you know. AI are pretty good at figuring this sort of thing out, you know, problem solved, right? Not so much. I mean, they are very effective. I'm not here to poo-poo anomaly-based intrusion detection systems. They're great, but they do have their issues. They are big, you know, clunky sort of pieces of software. They can often require dedicated hardware through your network. They have training time. You need to have 1-2 weeks of time where you actually have to sit there and tell it, okay, learn this as normal. You have to make sure that there's nothing unusual going on during that time, because otherwise it will learn the unusual as the new normal. And then you have to tune it, right? As the network use case changes, as the business you're working with, your clients, their use case changes, you have to change what normal changes. So you have to change what the AI actually sees as normal. So you have to constantly retune, and of course during this process you're going to get a lot of false positives. The other thing specifically with denial of service attacks is that you can detect a sudden burst of traffic, a sudden, you know, large amount of legitimate users using your website as an attack. Like, say for example, you're working with a web host that for some reason is hosting, I don't know, Steam, and the Steam sales start, and suddenly everyone visits the website. Now, an anomaly-based intrusion detection system might go, that's a lot of traffic, a lot of legitimate-looking traffic showing up at once. Yeah, it looks like an attack. And that can generate false positives, which can lead to alert fatigue, which isn't particularly good for your security department. We have a different solution, though. We call it PEIMA, the probability engine to identify malicious activity. So what can PEIMA do? Well, it's an anomaly-based detection system, right? So, you know, pretty good. It detects attacks within microseconds of them starting. It's accurate, doesn't have that problem where if you send a whole bunch of legitimate traffic, it confuses that with an actual denial of service attack. It knows the difference between them. It uses only metadata. Right, so you can actually do this without having to decrypt or do any sort of deep packet inspection with the traffic you're working with, which is great for privacy sort of things, and it doesn't require learning before it starts working. So it's basically plug and play. Well, how is that possible? How can it possibly know what normal is before we get there? Well, we use these things called, these are numeric patterns called power law probability distributions, which I'm liable to shorten to power laws during this talk, which isn't mathematically accurate. So if you're a mathematician out there, I'm very, very sorry. So anyway, power law probability distributions, power laws, they're these artifacts of natural number distributions and statistics. So anything, you know, natural number, bell curve shaped sort of thing. If a process generating numbers is statistically natural, then numbers that are generated or descriptive of it tend to fulfill these sorts of power law distributions. So power laws like this are very interesting. They show up in all sorts of weird places. There's some really good videos. There's a Vsauce video you should definitely check out if you're interested in this sort of thing. So what do we have? We've got like, this is the big granddaddy of them, the Pareto distribution. It was developed originally to explain the distribution of wealth in Italy. Basically, it's also really talked about as the Pareto principle, the 80-20 principle. 80% of the wealth resides in 20% of the holders. You know, 80% of the attacks go to 20% of your endpoints. 80% of your hard drive failures come from 20% of the hard drives. This shows up in all sorts of weird places. Now, it's great and it's very, very generally applicable, but it is a continuous distribution, which means lots of floating point calculations, and no one likes floating point calculations. They take too long. So conveniently, we do have discrete distributions. For example, Zipf's law. Zipf's law relates the popularity of categories to the number of elements in them. In its basic example, in any given book, if we rank words by the amount of times they appear, the second most popular word will appear about a half as much as the first one, and the third most popular appears about a third as much as the first one, fourth, a quarter of the first, and so on and so forth. This has been determined to work with any book in any language, which is pretty cool. It also works with other things, like city populations. The most populous cities do the same sort of thing. Species distribution over a certain area. So you give a given area, you check the number of each type of species. Game or movie popularity in a group of people. Twitter followers, and so on and so forth. It goes on forever. Anytime you can count a thing that is generated by a natural statistical process, Zipf's law comes into application. And we're not entirely sure why. All we know is that it does. Now, the interesting thing is this Zipf's law is not being followed by, say, a book. That means it's generally gibberish. And it's not gibberish as in random letters, because that does tend to follow Zipf's law. It means that there are real words. They're just arranged in a way that is gibberish. So, Benford's law. This one's really great. Benford's law actually doesn't change. For numbers, right, so it's interested in numbers, not categories, numbers generated by a natural process that are large enough, so they have to be the ability to be several orders of magnitude in size. That just means they have to be several orders of magnitude in size. So the probability that the first digit of that number that comes out of that process is 1 is about 30%. Right? Not 1 on 9 as you'd expect from a completely flatly random sort of process. Right? If you did this with, say, a pseudorandom number generator, you'd expect to see 1 on 9 for each of those digits. You don't see that in natural situations. The distribution is completely static. Regardless of which situation you apply it to, it is always going to be the same numbers. So you can actually hard code the thing, which is really, really cool. So really great for computation purposes. Now, it has been used for detection of anomalies before. It's actually been used in fraud detection in finances and the banking sector for years, because financial transactions are a natural process, and financial transactions follow Benford's law. So when it's not, you know that someone's done something a bit shifty with their finances, so you can detect fraud that way. So why is this interesting? Well, it turns out that network traffic is a natural process, for whatever reason, somehow. Numbers extracted from and descriptive of network traffic follow these power law distributions. Specifically, you know, whole packet length follows Zipf's law. The time between packet arrivals, inter-arrival times, follows Benford's law. Now, interestingly, both of those things that I just mentioned can be ripped out from packet headers. So you don't need anything more than that. You can just turn on TCP dump and away you go. When a denial of service attack happens, as we found out, the network stops being natural. And you end up with something like this. This is from a test network where we had multiple users actively using the network, and one user who was trying to stop them. So that was pretty fun. There are 10 distinct DOS attacks here, each one starting and then stopping before the next one. Mostly we did that because we didn't actually want to break the network while we were capturing data off it, and denial of service attacks that became pretty damaging. Now, these data points, each data point on these graphs, actually shows up every few microseconds. So it's very, very fast. This system can actually determine when an attack is started and stopped, almost as it happens. And the reason why is this. The top graph here is normal traffic, what you'd expect to see normally. It's not perfect, but it's fairly close. And the bottom is a flood denial of service attack. All right? Denial of service attacks fundamentally change how your network works and change the process that's generating the traffic. Right? This is incredibly difficult to fool. If you want to do this properly, if you want to hide this, you have to regenerate the original distribution. And that makes it basically impossible to do without breaking your attack. Now, explanation of why. There's an example back home in Australia, the March of the Red Crabs on Christmas Island. Each year, the red crabs on Christmas Island march across the island to the ocean to breed, right? They're land-dwelling crab species. There's thousands and thousands and thousands of them. Power laws apply to species over a certain area. So when the March of the Crabs happens, you end up with Zipf's law being broken in this case. There are far too many crabs in a small area. It completely overwhelms the distribution and breaks it. In order for you to return the power laws back to working again, you'd have to spread out the crabs so far apart that they'd basically be where you'd expect them to be. And at that point, are the crabs really having their year-long march, their once-in-a-year march? Are they really? Is there really an event going on anymore? Because they're sort of where they would usually be at any other time of the year. So that's really what's going on, is that breaking power laws is fundamental to both the march of the red crabs and DOS, DDoS attacks. Right? It is a feature of those attacks. So you can't do the attack very easily anyway, it's extremely difficult, without breaking these laws. Even if you time your attacks properly, you're still interacting with a gestalt of all of the traffic on that network. So it's incredibly difficult to manage to perform this attack without breaking these laws. So the fact that this is something you can hard code and then chuck a static threshold on makes this process really, really powerful for what you have to do. But wait, there's more. We can use these things as an intrusion detection system in general. Power laws are great at telling when a process is altered. All right, so attacks alter a network. That means we can detect them. What we have seen in our research is that Nmap and brute force style overflow attacks can be detected. Example is an NGINX buffer overflow attack. We can detect that. But we're doing it very crudely using thresholds. You could make this a lot smarter by strapping traditional detection techniques on top of it. So you could build, say, a signature-based detection system, because again, you don't have to now tell it what normal looks like. You know what normal for any given network looks like. You just have to tell it what each attack looks like, different to the normal distribution that you're looking at. So you could just build signatures for your anomaly detection system. So you now have an anomaly detection system sort of power level with signature-based detection system deployment, which is pretty cool. Speaking of detecting altered processes though, users are a natural process, because they're human, right? Language is a natural process, finance is a natural process. Humans just do things naturally. We're natural, we're from the natural world. So you can create unique profiles of users based on error from power laws. Not necessarily that they follow the power laws, but that their process is unique in what the error from the power laws is. So when the user changes, that profile you've generated changes as well, because now you've got a different process generating the information. We've seen this done in other research with key press latency timing, so the time between each key press. That follows Zipf's law, so you can actually check when a human's not using a computer, and also when a human, when any given human is actually using a computer. It also works with Benford's law, even though Benford's law does not come anywhere near with complying with that distribution. It doesn't follow Benford's law at all. But the error from it can be used to determine when a user has changed. Now this can be, this can theoretically be extended to anything a user has access to. So command usage, network usage. I mean, if a human is interacting with it, it's more likely than not going to be affected by natural processes. And even if it's not, again, because the human is the process generating it, you can detect when that process changes. So you can combine this with other analysis to start giving you an idea of how an attack is moving through your network. So you can sort of say, this user's been changed, I know this machine's been breached, so I know which account they got onto, where, this sort of thing going on. And again, this is minimal setup, minimal resource usage, and it's fast. So how do you use any of this? Well, PEIMA consists really of some power law-based analysis tools plugged into a decision system that can then take action. So like a normal IDS or IPS, right? Well, no. The sensors can be really, really lightweight. So, for example, in our prototype, we've actually got TCP dump as one of our sensors. So you can basically run it on the same machine as the decision mechanism. All we need are the metadata from the packets. All we need is packet headers. So it's really, really lightweight and fast. So the detection mechanism can just consist of a law that is hard-coded with a threshold that is hard-coded. So it's all integer math, so it's really, really fast and lightweight. The whole thing can be run on a household router if you need to. Now obviously that's going to get overwhelmed by any attack you throw at it because it's a household router and doesn't have very much throughput. But the point is you can run this on really, really small systems and scale it up to be a very, very low footprint on a really, really wide scaled system. So how can you actually use this? Well, the first thing you want to do is you want to find some metadata. You want to find some data you can use. Now, in terms of research, we don't know where this all goes. We don't know how much or what things, like the complete listing of all things that apply to these laws. So experimentation is really handy here. But we do know that network traffic and users are natural processes. So if you find something that's related to them, you're likely on the right route. Zip's law is really easy to find stuff for. Look for groups and categories. An example is that we haven't talked about yet is TCP flags. The amount of SYN packets, the amount of ACK packets, the amount of FIN packets, that sort of thing. So Benford's needs numbers, right? And they need to be of sufficient length. So look for things that can be many digits long that are related to these numbers that are generated. Be aware that sometimes zips and Benfords can converge and you can actually use the same data on both laws. So don't think that just because you have one you can't use another. This is actually possible to cross-pollinate. The next thing you need to do is you need to create analysis windows. Now statistical analysis needs batches of data to work with. So you need to group packets or group events together in order to do statistical analysis on them. You can't just look at one at a time. You can make them really big. You can detect really slow sort of long-term events happening in that case, but your sensitivity does decrease in that case. If you make them small, your sensitivity does go up, but you start losing your big events. And if you go too small, you start having breakdown your statistical analysis anyway. So it's okay to go big. You've got to be careful with going too small. In research, the best size we can tell is about 1,000 events or 1,000 packets each. But that's really based on some guesses and a sensitivity analysis. So really, again, experimentation with your specific usage is a good idea. So then you analyze your windows' respective power laws. You want to do something like a goodness of fit test. This is really, it sounds more complicated than it is. Really what you can do is you can take the differences between what you expect to see and what you've currently got, square all of those differences and add them all together, and that number tells you how far away you are from what you're supposed to be on. It's really, really simple, very, very fast. So then you pump those numbers into a decision mechanism, and that can be a threshold, a single number that if you go above, something bad's happening. That can be a signature-based system. That can even be a neural network you've thrown together. So then you want to, then you can also have that do things like alerting staff or taking direct measures or changing firewall settings or, so what have you. So a small example, you have PEIMA running on a gateway. It looks at the inter-arrival times on Benford's law. So it grabs packets, checks how far apart they were, checks that against Benford's law. It's got a hard-coded law in there. It's got a hard-coded threshold. Anything goes above, it configures IP tables to silently drop those packets. You've now got silent denial of service mitigation on that gateway. It doesn't require anything else. It just sits on the gateway. The whole system's totally encompassed in it. The second example, we can go with very, very big, the Eye of Sauron approach. You have a seam, you like your seam, you've set it up really nicely. It gathers data from everywhere. It gathers data from user computers, user data, it has network data, it has everything. You take that data, metadata or data from that the seam's collecting, put that into PEIMA, and then pass PEIMA's analysis back to the seam. You now have an alert, and PEIMA can say, this is bad. And now you actually have things like you actually now have a mathematical law of nature telling you, hey, something's wrong. So if you've got an attack going on and PEIMA's telling you it's bad, it's probably something actually going on. But if you've got an alert for a denial of service attack and PEIMA says everything's good, then it's likely, it's just a false alarm. Now, this will improve your system's ability to determine alert severity and reduce alert fatigue. So in conclusion, early days here. I mean, we're not entirely sure what the entire space of this is. It's not been completely plumbed, but what we have seen so far is reasonably impressive. Now, this is a wild west of anomaly detection right now. If you're an engineer and want to strike gold here, now's the time to experiment. These solutions are coming, and they will affect how you defend your networks. So, thank you very much. Hopefully you enjoyed hearing about this brand new method of anomaly detection, and you're reasonably interested if you're an engineer in playing around with this yourselves. Any questions? Yes, there's microphones there, and there. I mean, if you just yell it out to me, I can repeat it.
I didn't see how you could mitigate denial of service. How you can determine that there's an unusual distribution, and how do you know what part that is attack?
So power laws can be the nice thing about them is they're generally applicable to any subset of data you've got. So if you go, there's an attack going on, you can split up by endpoints, and you can go, the attack is going here and it's coming from here. Can you determine between, spoofed addresses and non-spoofed addresses that way? Not really, but at the very least you can have something that turns around and says, I know it's this IP address, I'm going to blacklist it for a little bit. Yes? Yep. So determining difference, the standard deviation from our attacks, the sort of error from what we expect, if it's built up slowly, won't we not be able to detect it? Well, that's the difference. This uses a solid law. That never changes. It never has to. That's always the same, right? We don't have to shift an average. We don't have to create an average. We know everything should be following Benford's law, for example. So if they start building up an attack slowly and, they start an attack slowly and build it up, at some point it will reach a point where it is so far from Benford's law that we'll be able to go, well, there's an attack there now. So unlike, having to build a, distribution, and then work with it all the way through, you can just work with these solid ones that we've got, and you can just work with that and it doesn't have to change.
Hi, I have a question. Can you go back to example 1?
Oh, example 1, sure.
And do you mind describing a bit more what exactly you use to apply the power law?
Okay, cool. So what we're doing is we grab the, you'd grab your packet headers, right? You don't have to grab very much out of them. You grab your packet headers, you figure out how far apart each one of them are. So how many microseconds have elapsed since the last one hit. You take
on
those.
A specific flow or across all?
No, it's across everything. This can work with any subset of data, right? You can use flows. You can also just use Gestalt data directly out of the network interface. It does not matter. It applies to everything.
So you're measuring time between when two packets arrive.
Yep.
And obviously that time will decrease as number of requests goes up, right?
Yep.
And what's the difference between your approach to just counting number of requests?
Because if you count number of requests and you're looking at normal traffic hitting you, that number will still be high. So you can turn around and say that that's actually an attack. In this case, the difference is that we are, because we're using the power laws, the number of requests aren't important. It can be a massive number of requests, but because they're split nicely following these power laws, even in a small way, we can determine that there's actually a difference between legitimate traffic and scripted, attack traffic.
But when you have increasing requests, your average time between two packets will decrease, which means it will break.
Yes, but it doesn't decrease in the same way that an attack does. One is inherently artificial.
Okay, thank you.
Thank you all for your interest in this topic. If we have additional questions, we'll be going to the speaker wrap room, and you can actually follow us there and continue your questions in that room. So I encourage you to please follow us to the speaker room if you have additional questions from this point. Thank you very much for coming.